The hell was that?
That was the countdown timer. We're live now.
You had that. That's cool.
I thought I did it last time. Maybe not.
I don't think so.
Well, that's good to know. Is that just stock music? Obviously.
Yeah, it's just built into StreamYard. I didn't make that. I'm not that talented.
Oh, we should. Okay. Well, now we need a theme song. Okay.
Oh, no.
Oh, yeah. So we're live?
Yes.
Right.
This is right? Okay. Hey, everyone.
So tell everybody why we're here.
Sorry?
I said tell everybody why we're here.
Yeah, that's what I'm doing. I'm doing the intro. Welcome, everyone. Thank you for joining live or watching in the archives, whether you're doing that. First of all, we want to wish and hope everyone had an enjoyable Martin Luther King Day and did something that reflects the great legacy of Dr. King and his commitment to social and economic justice. So for our friends in the United States, I hope today was a good day for you. This, of course, is Space Club XV, the extended voyage of what used to be a weekly pub chat with a gentleman I'll introduce shortly. Though none of us are now at that university or moved on with our lives for various reasons. So we decided to continue doing it. Times have changed, but we want to keep up to date, not only with each other, but more importantly, no, I shouldn't say that. We want to keep up with space exploration and more importantly with each other. I think, your friends are probably more important than the news. But we, of course, invite everyone else to join us. You're all welcome. And whether you're working in the field, whether you're a planetary scientist or astronomer or space policy expert or what have you, or you're just interested in space explorations, specifically robotic space exploration is mostly what we talk about here. This is the place for you. Welcome, join the chat, meet fellow space enthusiasts, whether you're new or old. I hope it's a wonderful opportunity to learn about what's happening in space and meet some other people. So without further ado, I'm Danny Bednar. I'm a part-time assistant professor at the Department of Geography and Environment at Western University. To pay the bills, I work for the Canadian Space Agency. Up above, we have Dr. Tanya Harrison, Martian geologist, doctor of Mars, looker-atter of Earth, scientist, artist, tweeter, overall space guru. Hi, Tanya.
Hello. That's a good intro.
And down below, we have Dr. Professor Phil Stooke, resident Salisburian, and the nicest guy in academia. What is the demonym for someone from Salisbury?
Oh, dear me. I am not sure about that. Salisburian?
Yeah, so
I don't know. Nobody ever asked me before. I don't know.
Salisburgian? No, that's Salzburg.
Salzburger? No, I don't think so.
No, that's what a Salzburg.
Yeah, that's right.
So let's get started. Phil, I'll ask you first. Who is the 114-year-old trans-Neptunian man?
Oh, well, that must be Clyde Tombaugh.
It is.
Hey, whoa. Speak of the devil. There you go.
Yes, I apologize. Phil, he would have known that anyways, but I did tell him we were talking about Clyde Tombaugh. So this week in space history, unfortunately in 1997 this week, January 17th, I assume Dr. Tombaugh left us. He, of course, is famous for discovering Pluto, the non-planet. We won't really get into that. Long story short, Pluto was discovered. They assumed it was really big. Every time it passed in front of a star, they decided it was a little bit smaller. Ultimately, for different reasons, then there was also a process by which we needed to decide what is a planet, what counts as a planet, what's not. The world came up with some categories. Pluto didn't make the cut. Ultimately, it doesn't really matter. Or Phil, I think you've always said it doesn't really matter if it's a planet or not. It's still fascinating.
That's right.
What I did want to mention is how Clyde Tombaugh found Pluto in 1930.
Right.
It relates to something you do, and it's blink comparison.
Yes, that's right. And I've done that many a time. So the basic idea is that you take two pictures. So Tombaugh would take a picture of a star field and then another picture of the same star field, and he'd get them lined up slightly better than that, hopefully. They're not absolutely perfectly lined up there, but as you blink between them, you can see things that are moving, and there are a few things that are moving in that image. So it gives you a clue that there's something is different there. So they found things that were moving, and then you look at another picture and so on, and eventually you confirm that one of these things is moving smoothly across the image. It's not just like a little speck of dust or something, but it's actually moving in a regular way across the image. So yeah, that's what he does, and I've done similar things, but not with pictures of stars.
Right. No, you do it with craters.
Things like that. Well, I did something like that to find the impact site of the Chinese orbiter Chang'e 1 on the moon. I had an Apollo 16 image of an area that was taken before the spacecraft got there, and then a lunar reconnaissance orbiter picture of the same area taken after this Chinese spacecraft had crashed on the moon. And you could see the difference between the two when you flip back and forth between them. Yeah.
Yeah, and these are the plates kind of digitized. If I'm not mistaken, this would be Pluto. This is the fascinating world of astronomy, kids. I don't know much else about what's going on here, but yeah, this is the blink comparison method that was used for a long time with telescopic plates, but still used today for surface feature detection, although often now automated with computers. Moving along to more news this week, something we'll be able to celebrate also this week, along with a few other things. Tanya, what do Neil Armstrong, Tina Fey, Homer Simpson, and Optimus Prime have in common?
I have no idea.
Oh, come on.
I mean...
They all shared the screen with one Edwin Buzz Aldrin. January 20th, 1930, actually the year Pluto was discovered. He'll be celebrating his 91st birthday on Wednesday, not birthday, actually. So obviously the most famous second person to step on the moon, or famous for being the first second person to step on the moon. Was also the first astronaut with a PhD. So the first couple intakes of astronauts, Buzz was a part of the third class, so to speak. The first few sets were all kind of test pilots, either Air Force, Army, or civilian. Buzz was also a fighter pilot, but had a PhD from MIT with a specialization in orbital rendezvous, which at the time was purely theoretical, but ended up coming in handy. So you never know, doing a PhD can actually come in handy. Waiting for that. So he, of course, Michael Collins would have done a lot of the work, but he certainly conducted the most famous orbital rendezvous of all time, probably on July 23rd, 1969. Fresh off of dancing around on the moon, he would have docked with Michael Collins in orbit around the moon and come home. His other achievements in his 91 years, short of 2 days, include February 24th, the birth date of my first high school girlfriend. But February 24th, 1994, he starred in Deep Space Homer. So guest starred on the season 5 episode of Simpsons, which is one of the greatest seasons of television history. But those of you in the space sector know that Buzz is around quite often. Unfortunately, with COVID and everything, there's no conferences going on. But hopefully when things get back to normal and Buzz's health, hopefully we're all hoping is fine, he'll be at conferences again. And a lot of us have had interactions with Buzz because of this. Tanya, do you have any Buzz stories from, I'm sure you've seen him at quite a few because he's been active with Space Society and Humans to Mars.
Yeah, it's certainly surreal the first time that you meet someone like Buzz Aldrin. Like growing up being obsessed with space, it's like you can't believe it's happening. And then you realize like the novelty wears off at some point when you work in the space industry, because you're like, oh yeah, Buzz is here, Buzz is everywhere. And that's also another weird feeling. You're like, oh, it's just normal now to show up at an event and Buzz is there. I think my favorite encounter with him was he came to ASU while I was working there at the New Space Initiative. And we had him giving a talk at some kind of banquet. I can't remember what it was for, but he was our keynote speaker. And you know, like you said, Buzz is 91 now, almost 91. And sometimes it's kind of hard to get him to stay on topic or give a very coherent speech these days. And he was supposed to speak for something like 20 minutes. He kind of went on for about an hour and a half or something like that, but no one wanted to stop him because they're like, it's Buzz Aldrin. We're not going to make him stop talking. And in the midst of his rambling, he had little good bits here and there. And there was probably like a 3-minute segment in the middle where he just like completely came together and gave this really beautiful message about like mental health. And I wish I could remember it now. I need to go back because I remember I tweeted the quote. I thought it was really beautiful, but because I mean, he struggled with a lot of mental health issues like after he came back from the moon. And so he talked a little bit about that and then kind of went back off into just talking about a bunch of other random things. But that one message in the middle was really beautiful.
Phil, how about you? I don't know if you've encountered Buzz, but I mean, you've been reading about the guy for over 50 years now.
Mm-hmm. Yeah, that's true. That's true. But I haven't actually met him. No, that's right. But well, he's certainly a very interesting character. And maybe apart from, you know, little things like landing on the moon, maybe one of the other things he was quite famous for was punching out a fellow who told him that it was all a hoax. Right?
Yeah, we'll actually get to that. Yeah, don't worry. You preempted me on that one. But yeah, I have a Buzz couple stories. To this day, a friend of mine and I refer to the largest moon of Mars is.
Sorry, your audio cut out there.
Oh, what is the largest moon of Mars?
Oh, Phobos.
Right. So to this day, a friend of mine and I refer to as Phobos because we were watching Buzz speak, and he continuously said we should land on Phobos as part of our infrastructure to get to Mars. Landing on Phobos, because Phobos doesn't have an atmosphere, would be relatively easy, and then we could telecontrol and things like this. So to this day, I still often use Phobos. Buzz says it. He also snubbed me pretty hard for a photo. We were in a conference. He sat down in front of me. You know, the session was wonderful. He actually spoke in that session about depression and alcoholism, things he struggled with, things I've struggled with, and I was very happy he did that. And I said afterwards, like, thanks for talking about that, you know, someone of your stature. And he said, oh, you know, it's my pleasure. You know, a lot of Air Force guys are my friends. We talk about it all the time. And it was a short little conversation. I said, like, oh, could I grab a picture? And he just kind of looked me up and down. I was like, nah.
Oh, dear.
I wouldn't have been like, I'm not bothered. I understand. He's a really busy guy. But he took pictures with other people leaving the room. So he gave in, or he knew the people, or I just gave off a terrible vibe. But yeah, he definitely stumped me for a picture, but that's okay. He's a good man. And well, obviously speaking openly about his depression and anxiety with his stature, with his background, very admirable.
Yeah.
Go ahead.
Oh, no, finish your share.
Well, I was going to transition.
Oh, as you asking me what the moon of Mars, the largest moon of Mars is, made me think of, there was one time back in the day when we were both at Western, and I think I don't remember where we went. We went somewhere to get drinks or something, and Danny made me take the exam for his class at the bar. And then he graded it in front of me to like judge really hard about like
I didn't
how
judge.
good I was in space. You didn't judge? I figured you were doing it to judge.
But you told people that was a date, which
What?
well, someone talked to me about like, didn't you go on a date with Tanya and make her take a quiz? Which sounded funny, but
I never said it was a date.
I never said it was a date either. So you told someone we went for drinks, and I was just showing you my teaching method, my teleology.
Yeah, I took all the exams for your class. I did really badly on the space history one, but I did really well on the planetary science one.
Yeah, you were a guinea pig. Phil, he'll get 100%, and I don't know if it's hard or easy. Although you're not necessarily a benchmark either, because you're a doctor in Martian.
Maybe I just cheated.
Getting back to Buzz, in a little bit, we're going to be talking about someone from Ireland. This weekend, the Pride of Ireland, Conor McGregor, will be fighting. Perhaps Conor's best weapon is his straight left, but Buzz Aldrin himself has a pretty decent straight right. So this is actually what Phil was talking about. This was back in 2002, so Aldrin there was 72 years old. And this person was going up to all the Apollo astronauts with a Bible and asking them to swear on it that they had walked on the moon. And then he was filming it. And in this specific instance, Buzz had been lured to this hotel under false pretenses that he was filming something for a kids' TV show, which he was like, oh, of course. No, I assume Buzz would for sure, film a quick voiceover or something. And then he gets kind of confronted by this guy. I gotta say, I don't know if Buzz has any formal boxing training, but this is a nice shot. I'm not advocating violence, but he's in front of an aggressive person. It's self-defense. There were no charges laid because of, it's very clearly him being aggressively pursued by someone much younger. He's 72, but he's wearing a suit. He doesn't wing his arm out too much. It's a decent straight right. He's not aiming to hurt the guy. You can tell he doesn't drop his shoulder. He doesn't turn his hips. He just gives him a little love tap straight down the pipe. And it's just, it's quite beautiful. He keeps his eye on the target. He creates a little separation. He parries the Bible. So the guy's holding the Bible and kind of poking him with it. Buzz lands the straight right and parries the Bible to the left. So a wonderful shot by a 72-year-old man, self-defense. But shout out to Buzz for one of his more other famous accomplishments well, it wasn't on television, but it shortly made it to television. Tanya, have you seen this before?
Oh, absolutely.
Okay, so let's move on. This will be a tough one. I'll open up to either of you. What do Huygens, Kepler, Lagrange, Galileo, and the Mafia have in common?
Ooh.
You're not going to get it.
Oh, you stumped me on that one.
Yeah.
Yeah, I don't know.
They all had biographies written by them by Mary Agnes Clerk, who passed away in 1907 this week, January 20th. She's from Skibbereen, County Cork, Ireland, home of the Skibbereen Arts Festival and Agricultural Festival. And she reminds me a little bit of all three of us, so I wanted to highlight her for This Week in Space. Phil, she reminds me of you. At age 15, she was fascinated with the history of astronomy, but didn't have access to any books on the history of astronomy other than a few things here and there at the library, at school. She wrote her own history of astronomy at the age of 15 to make her own version, so that she would have it at home. Very similar to what you did and what you read about in For All Humankind, teenage exploits of creating his own moon atlases. And her interest in astronomy probably came about potentially from her father, who observed the stars, but not for any astronomical reason. So this is late Victorian era. This is his job, and he's observing the stars regularly. Phil, any guess why someone in the late Victorian era might be observing the stars with no astronomical purpose?
I'm not sure what you're getting at there now.
He was developing means potentially to coordinate or synchronize clocks across time zones. There were early methods to use stars to some. There was a few proposals. You know,
okay. I had thought of that being done earlier than that, actually. But anyway, if you say so.
You don't sound convinced. Anyways, he was after continuing these methods. Of course, now we still use space to synchronize clocks across the world and around the world and across time zones with GPS satellites. But Mary studied in Dublin, Italy, and ended up in London as a popular science writer. Well before her time, not just a female writer, not just a popular science writer, but a female popular science writer. Popular science writing at the time limited. In places like London, it might have been more popular, but certainly a trailblazer in that regards. Very impressively, her 1885 Popular History of Astronomy was a definitive text in the history of astronomy. It ran for 4 editions. 135 years later, it's still quite relevant. Of course, a lot has happened. A lot of research has taken place since then. And impressively, she actually became an astronomer herself. She studied in an emerging field, stellar spectroscopy, so kind of figuring out what stars might be made of based on what their light looks like. And she published in that area in 1888. So she went from kind of a self-trained popular science writer to a kind of definitive historian to a published astronomer. And she became the third female member of the Royal Astronomical Society in 1905. And to this day, we can see a nod to her on the moon. So this is one of Phil's maps that he presented in an old Planet Club / Place Club, and I stole it and use it in my course all the time. But if you see Mare Serenitatis, I never get these right.
Yes, that's right.
Near the bottom right edge, near where Apollo 17 landed, there is Clerke Crater, and you can see here where Apollo 17 landed. So it's actually quite close by.
Mm.
And last but not least, we'll have to do this quickly. Tanya, what happens when you start getting forgetful on Mars?
You got to reboot.
Yeah, sorry, go ahead.
So back this week in 2004, the Spirit rover had what we call the Sol 18 anomaly. And on Mars, we call days sols, short for solar days, since the day's a little bit different than it is here. It's a little bit longer. And after Spirit landed, it was working remarkably well until Sol 18, when the rover didn't respond to any of the commands that were sent to it. And so a couple days went by. The engineers tried to investigate what was going on. They were sending signals and not getting a response. They could tell that the rover wasn't entirely dead. They could see that it was still there, just not responding. But as a couple of days went by, it started to cause a bit of worry because the temperature on the rover was getting too high. So it looked like the rover wasn't sleeping when it was supposed to. The rovers actually only operate for a few hours every day, both to conserve power from the batteries and to keep the electronics from overheating. That might seem strange on a place like Mars where it's really cold, but Mars doesn't have a lot of air to help conduct heat away. And so you actually have to worry about overheating quite often. And it turned out, I'm going to put the command that was sent to the rover on a banner here because it's so perfect. The engineer sent this command, which is actually short for shut down, damn it, until. And then they would tell the rover when it was supposed to wake up. So they were trying to basically reboot the rover by commanding it to sleep and then waking up again. And luckily, after about 3 sols, it worked again. It turned out that there was a problem with the flash memory where the rover wasn't clearing it out in time. And so in the mornings, it was getting stuck in this weird reboot cycle. And then the rover continued to work pretty well for the next few years until it got stuck in some sand, turned into a lander for a little while, and then we finally lost contact with it in 2010 after it was only designed to last for 90 sols. So yeah, it's still a pretty successful mission.
And one thing I might briefly add about that was that the whole thing was being done under intense time pressure because Opportunity was approaching the planet. It landed about 3 weeks after Spirit. So it was approaching, and really what they wanted to be able to do was to give all of their attention and all the communication bandwidth and everything to Opportunity as it was approaching and landing. And they had to keep taking time out to do this. So it was a very tense time.
And we'll hear a little bit just in a moment about more ingenuity from the JPL engineers in regards to news this week. So that's it for This Week in Space History. Let's move ahead to some quick space news for the last month or so since we last left you. For a full rundown on 2021, check out our episode from 3 months ago, The Coming Year in Planetary Science. But this week, we'll just hit some of the big 4 missions that are underway. Starting off with Chang'e 5. So Thursday, December 17th, just before the Christmas break for a lot of us, China returned the first lunar samples since 1976's Luna 24. To do this, speaking of Buzz Aldrin, it completed a complex rendezvous and docking in orbit, as well as a robotic sample transfer. So a lot of impressive engineering there with the Chang'e 5 program. If I'm not wrong, correct, Phil?
That's right. Yeah. Mm-hmm.
And so we just found out this morning, but initially they had estimated 2 kilograms of lunar material, rocks and dust, or what we call regolith, essentially sand, soil-ish material. That's been revised this morning to 1.731 kilograms, about 3.8 pounds of moon rocks, moon material, from the Mons Rumker area in Oceanus Procellarum. So China has expressed that they're planning to share all of this materials and information with the scientific community, as is traditionally done with all sample materials from other planets and moons. And some more good news, Chang'e 5, the orbiter has been extended and is moving out to the Sun Lagrange point 1, which is a stable gravity well out between the Earth and the Sun. Anything else to add on Chang'e 5, Phil?
China just released guidelines for how people can apply to get some of the sample for analysis. But so far, there hasn't been any announcement about the results of any analysis.
Great. Let's move ahead to the big rover on Mars right now. Of course, it's waiting. Its cousin Perseverance will be on the way. But here we see Mount Sharp, which is a giant, well, fair-sized mountain by Martian terms in the middle of a crater. And this is where Curiosity is. It's slowly making its way up the mountain. The mountain itself is 5.5 kilometers tall, or 18,000 feet, roughly a third of the height of Mount Everest, or sorry, 2/3 the height of Mount Everest. Well, I don't think Curiosity will climb to the summit, but last I checked with Curiosity from Phil's posting online is it's recently celebrated its 3,000th sol, and it is here on Mars. Am I right, Phil?
Yeah, it hasn't moved since that was made a few days ago. Yeah, today is Sol 3005, and it's still there.
Wow.
So we'll talk about this next month, because next month we're doing a lot of Mars stuff. I'm correct in assuming it's not going to the summit of this mountain or anything like that.
It won't make it to the summit, no. But all of the interesting stuff is in the lower slopes anyway. The top part is not as interesting geologically. So
Depends on if you're a fluvial geomorphologist or an aeolian.
Yes, I suppose that might be true. It's not going to last long enough to get to the top anyway.
The wheels are going to fall off and the battery will be long before that.
Yeah, that's right. I think the power supply will be the ultimate control on its longevity. Yeah.
So what Tanya was just saying is Mars nerd talk for whether you're interested in the surface being changed by liquids, probably, or the surface being changed by winds and erosion, competing Mars camps.
Well, this is why Gale was one of the interesting sites for us to land. The bottom half of the mountain in Gale, Mount Sharp, is carved by channels and there's canyons in it. You can tell that it's been altered by water. But the top part of the mountain looks like it's just wind emplaced sediments. There's no evidence that it was affected by water at all. And so the thought is that this mountain actually straddles the transition from warm, wet Mars to cold, dry Mars. Unfortunately, like Bill said, we won't actually get to that transition point, which would be really incredible to see if we could look at either side. But it's what makes Gale really exciting.
Well, actually, I think we will get to the transition, but we
Really?
won't be able to get to the top of the mountain. But that top of the mountain is several kilometers of just the aeolian stuff. But I think we'll be able to get to the transition.
I didn't think we'd make it that far. That's really exciting.
No, I think so.
Those engineers at JPL, they can land a rover on Mars, but they can't even drive a 6-kilometer mountain. Speaking of engineering ingenuity, good news, bad news for Mars's probe lander on Mars. NASA's probe on Mars. It's the InSight probe, which is mostly looking for kind of seismic activity. So bad news first, after 759 Martian days, the mole, which was a little thing that was going to dig into the ground, is unfit to compete, so to speak. It is broken. You can see here the scoop, as Phil has talked about in past episodes, trying to hammer it in. That was unsuccessful. There may be some issues with the solar panels as well, and issues about whether or not there's enough wind to clean them off. Good news, mission extended for 2 years. So that means the brilliant engineers down there at JPL are funded for another 2 years of work to keep this thing going and keep learning about Mars quakes. Anything else from you two on InSight?
No. This little video is the most recent attempt to try to push that mole down, but it's although some sediment is moving around, the mole isn't going down, so they just decided that it's not going to go.
Yeah, it's quite unfortunate since this was going to be one of the big new pieces of Mars science that we would have gotten out of this mission.
Yeah,
we're trying to figure out if there's any internal activity left inside Mars, and we've never had a measurement like this before. So it's really disappointing, but I mean, the discovery of Mars quakes is still really, really cool and really significant.
Yeah.
Excellent. And last but not least, we have our newest Mars rover. By our, I mean humanities. I have nothing to do with this mission. Hurtling its way towards Mars right now, hopefully peacefully snuggled within its little capsule. Next month, we will do a deep dive into Mars rovers, possibly Perseverance. We'll decide that in a couple of days. But yes, Perseverance is scheduled to land with its little helicopter friend there on February 18th, roughly 12:30 in the afternoon Eastern or Californian time. These things are dictated by Martian time. Yeah, Phil, any quick things to tease next month?
Well, I guess we'll just have to hope that everything goes according to plan. But I would hope that we'd be able to say something next time about the very early activities. If I remember from curiosity, though, it took them more than 2 weeks to move at all. They spend a lot of time, well, first, of course, imaging the surroundings and making sure that they understand where they are and what they, what the surface is like, but also just checking out everything in the rover. It takes a while before you're actually driving anywhere. Maybe we'll just get to see the very first little bits of activity on the surface, but knowing it's down safely would be a good start.
Yeah, and as long as at least one camera opens up, we'll have something to talk about. And as I always tell my students, and as Phil instructed me, the first thing a rover takes a picture of is itself.
Itself? It's probably
make sure nothing's broken. I mean, it's good to know where you are, but you want to make sure you survived the landing process, which is quite cool. If you're interested, I posted in the live chat, the first message there is a video of how this thing is going to land. We'll go over that after the fact, hopefully, but it is a really cool 3-minute video, including a crane that hovers over Mars and drops this little thing. It is one of the craziest things you'll ever see. Whether you're really interested in Mars rovers or not, check out that video. And the landing will, I'm sure, be live streamed on NASA's Facebook page and Twitter. Yes. So if you're interested, February 18th, tune into that.
You should also tune into the We Martians live webcast, where Jake Robbins and I will be live talking to a bunch of different people involved with the mission before landing.
Yeah.
Oh, well, there you go. Some cross promotion.
Yeah.
You'll have to pitch then Space Club episode 7.
We'll do. I'll cross promotion.
Yes, when you're on We Martians. Before we move to the deep dive, are there any questions in the chat?
So Zaid was asking about the soil features that posed an issue for the drill. Granted, Cass also responded with the answer of the ground was just a lot harder than they bargained for. And I saw some chatter about this on Twitter, actually, from some folks that are used to working in permafrost type ground in places like the Antarctic dry valleys. And they said that the drill was not well designed for ground like that. And so if they had been consulting a little bit more with people that were used to working in the type of ground, they could have told them that the type of drill that they were using, well, the type of hammering mechanism they were using wasn't great for ground that they might expect at a place like where InSight landed. But we also encountered terrain that, or the dirt there wasn't exactly like what we had seen at other landing sites. So it's not like this was completely, it wasn't a complete oversight. So we just learned something new about soil on Mars in the process.
Mm-hmm. Yeah.
All right, is that all the questions?
I see one of your students must be here.
I see that too. Hey, and grades are already in, so that's not sucking up or anything. That's just genuine admiration of my teaching.
Yeah, there you go.
Okay, so I promised Phil 30 minutes for the deep dive, and we're at 35. So only 5 minutes. That's only 1/6 over. That's not too bad. So Phil, take us into the glorious 1990s mission when Friends was the top show on TV and everyone was listening to Ace of Base. Our successful failure at Jupiter.
Okay, well, yeah, let's go on. Galileo was this great Jupiter mission. First, I show a couple of slides very briefly of what went before it. There were two spacecraft called Pioneer 10 and 11, that made a very quick reconnaissance of the Jupiter system, and one of them went on to Saturn as well. Really, that was to show that you could actually get through the asteroid belt safely. These were the first things that ever did. And that you could actually get past the radiation belts of Jupiter safely. And again, they were the first things to do that. And the information they provided was useful for the next probes. And if we go to the next slide, so again, before Galileo, they were the Voyagers. And these did a lot more to really open up the Jupiter system. They showed us so much about what was there. Galileo then was designed to follow on from that. So Voyager, for instance, discovered that there were volcanoes on one of the moons. So Galileo then is going to make repeated observations again and again and again and again, monitoring that activity and looking at it in much more detail. So it was that sort of arrangement. So
is this a plume, Phil?
Yeah. So that picture, that is the discovery image of volcanoes on Io. And it wasn't even taken for scientific purposes. That was a navigation frame. They took that picture basically so that they could see where the moon is relative to the spacecraft as a way of helping to navigate it. They take a lot of pictures like that as they fly through. So you take a picture like that, and then you want to use an automatic routine to fit a circle to it so that you can define where the center of the moon is. And the automatic circle fitting routine didn't work very well because there was a great big lump sticking on the side of it. And their first thought was, that's going to be one of the other moons. Maybe that's Callisto off in the distance. But when you look at where the moons are, there was nothing there. And then they started to realize that this was a volcanic eruption on the moon. With that, I remember that it was several days after the flyby before people figured this out. And it was really a pretty special moment. Yeah, very exciting. And I suppose I could say that in the lower left image there, which has a kind of funny sort of heart-shaped pattern on the ground with a dark spot in the middle, that is actually that volcano. So the eruption is coming out of the dark spot in the middle, and it's rising up in the air and then falling down around the outer edges to make that that larger loop all around it. Okay, so that was Voyager. Now we go on to Galileo, which is named after this fellow, Galileo himself, who in the very beginning of the 17th century, looked at Jupiter with a telescope and saw 4 little spots beside it. And when he looked again, they'd moved a bit. So he realized that they were they're there with Jupiter. They're moving along with Jupiter in the sky, but they're moving around it as well. The first discovery of any planetary satellite. So the spacecraft named after him. Here it is being launched by a space shuttle, one of 2 planetary probes launched by a space shuttle.
No, hold on. To Venus.
Magellan was the second. Yeah.
Yep.
Right. That's right.
No.
So yeah, here we are, launched on Atlantis. And a lot of people were nervous about that because you can't go from the space shuttle sitting in low Earth orbit to Jupiter without having a great big rocket to push you there. So that's the thing underneath the probe there. The thing with USA written on it is the upper stage rocket. So the space shuttle has to launch basically with many tons of high explosive fuel nestled in its cargo bay. And it was somewhat nerve-wracking, but of course everything worked fine, and off it went.
Was there any practical reason to do that, or was it entirely political?
Well, it was really political. It was NASA was spending a lot of money to develop the space shuttle, and they wanted to find as many uses for it as they could. And it may indeed have led to the demise of Galileo. We're going to discover shortly that all was not well with the spacecraft, and that's partly because it had been built in JPL and trucked across the country to the Kennedy Space Center, and it was going to be put on a rocket, put into the shuttle and launched. And then there were serious problems, including, of course, the Challenger accident, which delayed flights for quite a while with the shuttle, which basically caused a long delay for Galileo, and it had to be trucked back across the country again and so on. The storage and possibly the transport might have contributed to the fact that its antenna got stuck in an unopened position, which we'll see shortly. It's not necessarily clear that's true, but there was a serious problem with that spacecraft. So let's go on.
It's interesting you mentioned, like, this is a bomb in here.
Yeah.
The shuttle itself, like, this is a giant liquid nitrogen, liquid fuel bomb. These are two little missiles. The whole thing was just a gigantic, dangerous system. But yeah, adding another one is an interesting choice.
Okay, so here's a couple of artists' impressions. There, up at the top, you see what Galileo was supposed to look like, and down below what it actually did look like. And basically, they look similar, except for one thing, and that is that there's this big antenna, which was a kind of a wire mesh antenna that is folded up against that central column there, and then it was supposed to open. But some of the ribs that helped to define the shape, some of those ribs got stuck, and you know, the ones at the bottom in the lower image, which haven't moved off of the central support. So half of it was opened and half of it wasn't, and they did everything they could to try to move that, but it never did open. And as a result, they could only transmit a tiny proportion of what they needed to. I'm sure somebody's got a proper number for this, but I would guess that it was far less than 1% of the actual number of bits that they really intended to transmit.
I have it. I was doing reading. I was doing research. So the low gain antenna, the small one, could do 8 bits per second. With the large, they were expecting at least in the thousands of bits per second.
Right.
So as Phil will explain, they ended up relying on the small antenna, which is 8 bits per second. So what could have been essentially HD streaming of at least pictures turned into the worst internet connection you could possibly imagine.
Yeah, that's right. That's right, yeah. And so basically, you have to figure out some way of dealing with that. So one thing is that instead of transmitting images in their highest quality, you transmit very compressed images. And these days, we all get to see that happening with video streaming and so on, when things slow down and they, you know, you're not getting the picture that you want. So they had to compress images. So practically everything that came down was very heavily compressed. As much as they could get away with, and if they needed something that wasn't compressed, there had to be a really good reason for that, you know. So a lot of stuff was very compressed, and they tried all sorts of other tricks as well. For instance, the images were 800 by 800 pixels. So what they would do was they would transmit a very, very condensed version of it. In fact, what they would do is they'd transmit one row of pixels, and then another row a bit further over, and another row. So they transmit maybe 10 rows of pixels spread across the whole image. And that way you can see whether the target that you want is in it. Like if you're taking a picture of a moon, is the moon actually in it? And where is it? And once you've found it by looking at those sparse rows, then you can just transmit the little bit that has got the target that you want. So quite a lot of images that came down, all they did was to transmit the little window with the bit of detail they wanted and not the whole image. So there are all sorts of little tricks that they played. But because, although they couldn't get very much back, they chose what they got back very carefully so that they could meet as many of their goals as intended. And they did pretty well with that.
Yeah, and what they ended up doing was they would wait for close passes of one of the moons or Jupiter take good pictures, store them on what little stores they had, and then while they were waiting for the next close pass, they would do what Phil just said and send what they could back with their really crappy connection. What they would have been doing the whole time is imaging as much as possible.
Oh yeah,
those passes the way orbiters typically do. They ended up having to just be a close pass imager system, which works, but obviously is not ideal.
No, and it's really interesting to compare that with Cassini, which worked perfectly. So Cassini is exactly the same situation. You fly past a bunch of moons and the rings and the planet and so on. You get lots of data and you transmit it back, and then you're going out the rest of the orbit and you can go and look at other things like distant moons or sort of continual monitoring of the Saturnian atmosphere or something like that. With Galileo, they might make a close flyby of one of the moons, but instead of filling the memory with 200 or 300 images and then getting them all back and then taking a whole bunch of other stuff, they might only take 20 pictures in one orbit. And those 20 pictures then took a month to transmit. And you're not doing anything else while you're doing that. So that's the kind of situation they were in. But they did get those 20 pictures, and then you do another orbit. So you just have to pick your images very carefully, and you compress them as much as you can anyway. And, ultimately you make things work.
Yeah, and the last thing I'll say on the high gain antenna that didn't unfurl, they knew that it had partially unfurled. Because there was a solar sensor on board that was being blocked. And they knew the only way that could happen was if the antenna had partly unfurled, because when it was going to unfurl, it was going to block it. And they knew that. So they knew that it had started the process and something got caught, jammed, whatever. And it's kind of heartbreaking. I was reading Jeffrey Kluger's book. It's called Journey Beyond Selene, which is about exploration of all the moons of the solar system. It's already 20 years old now, but he describes the head engineer who knew this system like the back of his hand, and he's just thinking, just like something you built yourself, every little part of it. He's just thinking, what bolt is it? What little screw is it? What is up? And there's nothing you can do. It's 5 acres away at this point.
That's heartbreaking.
Okay, so we'll have to go through this pretty quickly, but basically they looped around the solar system several times. They managed to fly past Venus and the Earth a couple of times, and then a couple of asteroids. So let's go on there. Here we've got an image, infrared image of Venus at the top. So they got some useful data every time they flew past something. The stuff they did for the moon was really quite useful, including these infrared images of the moon. These days, we're kind of fairly used to seeing pictures like that, but they were quite innovative for that time. So we got some good stuff anyway. It wasn't just a sort of a useless exercise and flying past Earth to get the gravity assist. You also got some good data. And now let's move on. Here they flew past an asteroid. This was the first asteroid ever visited in space, so it was a real big first for the mission. A little thing called Gaspra. Better go to the next image.
Did you map Gaspra?
Yes, I have a paper on that. Yeah.
For those of you who don't know, Phil maps weird shaped things. That's what he's most famous for.
Yeah. So my maps of these things are in the NASA's planetary data system. I did IDA as well. For this one, they flew past Ida and discovered quite by chance that it had a moon. And this was one of these things where they were just transmitting these individual little strips of an image to see which pictures actually had part of Ida in them. And one of those little strips had a funny little blip off the side of the asteroid, little something in it. So they realized there's something else there, and then they get the whole picture, and there's this little moon. And it was completely unexpected. The first asteroid moon ever discovered. We know lots of them now, but this was the first. Really interesting observations. And then this is something it's easy to overlook about Galileo, but it did something quite amazing as well. Back in 1994, a comet, which had been captured by Jupiter, broke up into multiple pieces, which continued orbiting Jupiter and then struck the surface. And so if you imagine that line of comet fragments zooming in towards Jupiter and hitting it one after another over the course of several days. And each one makes this big dark spot, which you can see in a Hubble telescope picture at the bottom there. Well, once the comet was discovered, people realized from its trajectory that it was going to hit the planet, and they had months to prepare for it. And the Hubble Space Telescope was available and so on. But Galileo was the only thing that was in the right place to actually see the collisions. The top row of pictures are from Galileo, and you can see a little dot beside them, beside the planet there. It hit on the dark side, and from Earth, you had the view that we have at the bottom there, where you're not actually seeing the dark side. It's almost a full phase. You don't really see the dark side. So the impacts happened in a place that couldn't be seen by Hubble or by ground-based telescopes. Galileo was the only thing that was in the right place to see it. So it took, even though it was far away, but it could get an observation, and you could look at the rise in brightness and then the decay in brightness of the flash and get some information from that. So it was an interesting event.
So this is Galileo's view looking back at Jupiter, and then it sees this flash like a nuclear bomb. No.
Yeah, and then a bit later on, Hubble takes the image, and it can see the debris in the atmosphere of Jupiter there. Wow. There's two separate strikes there. Yeah. Okay, so they naturally studied Jupiter itself, so there are quite a lot of pictures of clouds. But this is one of the things that was particularly hit by the antenna problem, because there would have been tens of thousands of pictures like these, tens of thousands, if the mission had gone well. Because when you're close into the planet and you're flying past the moons, you're studying them. But when you pull away and you've transmitted all that stuff, you've got time to look back at the planet and take lots of pictures of it. And that's what Cassini did. But for Jupiter, those images of the planet were basically almost all pushed aside just to slowly transmit all of the other data. So we didn't get anything like the amount of stuff that could have been done, but still quite a lot. Yeah. Okay, let's go on there. The spacecraft carried a probe which was dropped into the atmosphere. It was released, I think about 6 months before the spacecraft arrived at Jupiter. So it released quite early, and it just zoomed in and hit the planet, and the spacecraft then diverted itself so it wouldn't zoom in and hit the planet and went into orbit. And of course served as a relay for the data. And that probe, it entered the atmosphere, it descended on a parachute for about an hour, studying the physics and chemistry of the clouds and transmitting that data back. They didn't find as much water as they expected, and this is something that's only recently been understood, because people thought, well, maybe we just landed in a place that was drier than usual. And now it seems that we understand from a new spacecraft, Juno, that is there, that actually the whole atmosphere tends to be drier, or at least the upper atmosphere tends to be drier than we'd anticipated. So maybe Galileo's data were more typical than people had thought at the time. So far, that's the only probe in the atmosphere of one of the outer planets. Now let's have a quick look at the moons. Here's Io. This is the one with the volcanoes. On every orbit, when they could do it, Galileo was able to monitor the volcanoes. That row of pictures at the bottom showed the same place, and it's actually that same place that we looked at in one of the earlier Voyager images, with an eruption happening in the dark spot in the middle, and then the stuff sort of goes up in the air and then falls down around it to make the reddish circle. Red is sulfur. But you can see that each picture looks different because there are eruptions going on all the time, and not just from that, but from other ones as well. So you see changes constantly. Yeah, it's a very, very active surface. And we also got infrared images that showed the plumes and hotspots on the surface. Lots of them, so we can see some in that picture. And on the right, you can see an image that has another volcano rising above the horizon there into space. Yeah, so that was a significant part of what the mission was all about. But let's move on and look at the moons here because they're all interesting. Here's Europa. This is an amazing place. It's a little bit smaller than our moon, but it's covered, and it would be a rocky world inside it, like our moon, although a bit smaller. But it's surrounded by an ocean of water, probably 100 kilometers deep, and on top of that, an icy crust. So the upper part's frozen. And what we're looking at is the fractured ice layer over the top of the moon. So it's just covered with fractures like that. And because there's an ocean, well, it's conceivable that there could be things living in it, or at least biological materials in it. So it's become one of the favorite places for people to think about looking for signs of biology in the solar system. Let's go on. Here's a close-up of it. One thing that I always find hard to get my head around is that all those lines are actually ridges. At first I want to say, oh, they're cracks, they're depressions in the surface, but no, they're ridges sticking up. And you also get these sort of broad bands. And if you take those broad bands, like the one that runs across the middle of that picture, it looks smooth. It's quite wide. If you take that and you try to, you could imagine cutting out the top part and sliding it over and seeing how it matches up with the part below. And you can actually make things line up really well like that. So it seems that the surface has actually fractured, and the parts have drifted apart like the continents do on Earth. So a very interesting place. And we're not seeing craters. We didn't see craters on Io either, because they're all covered up by volcanic activity. And we're not seeing craters here because the surface is so active, constantly being broken up and things happening to it. So very few craters. But now we'll move on to a place that has a lot more craters. This is Ganymede, the next moon over. And it's the biggest moon in the solar system. It's bigger than the planet Mercury, but a very different looking surface. And again, it's got lots and lots of fractures on it, but there are also quite a lot of craters. So it's an older surface. And really quite a dramatic and interesting place. Yeah, okay, and here's a close-up of Ganymede. And this is another of these places where there's a smooth band, it's brighter this time, running across the center of the image. But the two sides, if you move them together, you can see how they line up. And these haven't just pulled apart, they've also moved sideways, but they actually do line up. And if you do put them back where they belong, then you can see the fractures running across the gap, and even craters that have been cut in half by the fracture, and the two sides separated, and you can actually see how they fit back together again. So again, there's been some sideways movement, like kind of plate tectonics on Earth. Yeah, so an interesting place. The moon, it's the only moon that has its own magnetic field, rather than something just induced by the planet. Oh, and here's Callisto. This is the fourth of these really big moons. And this one really is covered with craters. It's had far less actually happening on it than the other moons. So in a way, it serves like a kind of control for what these kinds of moons would be like. This is almost as big as Ganymede. It's almost as big as the planet Mercury, and just completely covered with craters. The very biggest impacts have smashed into the surface, and it's as if they've kind of sent out ripples into the surface, which have frozen in place. I don't know that that's really exactly how they formed, but it looks a bit like that. Ripple rings around a little smooth patch in the lower right. That's a really... Sorry? No?
No.
You okay?
Gotcha. Yeah.
Oh, okay. There we go. Yeah, and so here's a close-up of Callisto. There are lots of craters in the previous view, and you'd expect to see more here. But what happens when you get really close in is that you find that the surface has been affected by the ice kind of evaporating, or subliming, we should really say, away. The ice just turns into vapor and drifts away, leaving anything that was in the ice, like little bits of meteoric dust and stuff on the surface. So it has a dark surface, but the surface is gradually evaporating away like that. And it makes it smooth in places, but also it leaves these spiky hills. So I think that this is the kind of thing where you could imagine if you had say a meteorite or something, some rock sitting on the surface, or a block thrown out of a crater, and it kind of protects the surface around it as that's evaporating away. So you get these residual hills.
That's cool. It's kind of like the Callisto version of a glacial erratic when glaciers leave giant boulders behind when they melt.
We'll wait for Phil to reconnect here, but he's going to jump into these smaller moons, many of which we had no idea existed until Galileo came around. Phil, are you back with us?
Oh, I think I am. It feels like I'm back. Okay. Okay. All right. Okay. So there we go. Lots of little moons. Jupiter has many small moons. Most of them are far out away from the planet, but 4 of them are close in, and this shows some of them. And at the very end of the mission, there was a close flyby of the one called Amalthea, but close-up images were impossible because of radiation dam. That they tried to take them, but it didn't work. Time. Anyway, they had a close flyby. So here we see just a little bit of information about the rates. Yeah. Okay. So, that's it. And we're losing it. Yeah. Oh, okay. There we are. End of the mission. The spacecraft crashed. His
audio's breaking up, but yeah, when
Galileo nothing went right for me. All right. So at the end of the mission, they just burned up in the atmosphere. The spacecraft did to burn up so that it wouldn't hit one of the moons and contaminate it. But it was a good mission. We just didn't get as much back from it as people would have liked. But still, we learned a lot. And a couple of quick flybys.
Phil's breaking up again, but he's talking about, of course, we did get images of Jupiter
to monitor volcanoes on Io. Now we have a spacecraft there called, which there was one infrared image that has lots of volcanoes and hotspots on Io. It's sort of lower center, and the weird thing on the right is an infrared image of the auroras, the northern lights, the north pole of Jupiter.
Oh,
that image looks like the gates to hell or something.
Yeah, that is as you're talking about one of the storms in infrared. Jupiter's a scary place. When you look up close, it is quite terrifying. And yeah, in some of these other filters, it looks like hell.
Oh, okay. Are we back?
Yeah, you jumped.
Yeah. Okay, well, hopefully the images told their own story.
They do. They do.
Danny covered for you really well.
Oh, okay. Well, that's good. Okay, yeah. So it was a good mission, but just didn't give us as much as we would have liked.
I forgot that it lasted for 8 years.
Yeah.
Yeah.
Yeah. Yes, Aurora Borealis of fire, indeed. Yeah. It's quite a dramatic picture.
We've run slightly over, but does anybody have any quick questions before we wrap things up tonight?
And there's always surprises at the tops of these gas giants. Saturn, of course, with its famous hexagon storm, which is shaped incredibly like a hexagon. It is a natural phenomena that you can actually create with a bucket and fluids and just stirring it. You'll actually get a hexagon, which is cool. But yeah, the Galileo mission and future missions that have flown past the gas giants are always seeing somewhat terrifying imagery, but the gas giants are cool. There's nothing else. We will wrap up and let you know that hopefully February 18th, the space exploration community will be holding its breath, and hopefully everything goes well for the team at JPL, Caltech, NASA, and all of the other teams involved with that mission from around the world. It is truly a global mission. There are teams from across Europe and North America participating with their instruments on board the rover.
Yeah.
Of course, the main operations take place out of JPL Caltech over in Pasadena. So hopefully everything goes well. Right now, a lot of it is up to what's already in place. There's not too much that you can do anymore. But February 20th, around 12:30. And Phil, do you know if it's California or North time?
I don't actually know. I'll have to check.
Yeah.
I
But
can't remember either.
if you're looking for it, it'll be easy to find. Tanya will be tweeting all about it. And like she said, she'll be on the We Martians podcast talking to a lot of the mission. And
we've also got the Tianwen mission arriving next month and the Hope mission from the UAE also getting to Mars. So next month will be really exciting for Mars. That's
right. Yeah. So actually the Chinese mission goes into orbit, but it won't land for a couple of months. They'll take some time to image the landing site from orbit before they go down to the surface.
Yeah, they're pulling a Viking, which is interesting.
Yep, the Mars window is open, as we say, which is just to mean that Mars is close enough to relatively cheaper and faster land on it more efficiently. So, yeah, this week or this month will be exciting. And yeah, if there's nothing else, we'll sign off and see you next week. Here.
Next time.
Right. Well.
All right.
Tanya,
thanks,
Phil.
everybody.
Okay. Bye, folks. Okay. Bye.
See everyone.